Okay, 3-7. I know in 3-6 I said it was the end, but I promise this is the last of Unit 3. 3-7, I know I say I like a lot of the sections, but I love 3-7. I think it is so cool what you guys can do with these problems. Yes, they're story problems. Don't groan. They're going to be fun because you can find out some really cool information. Okay, so there's 3 ways to do these. I'm going to go over a simple problem and show you all 3 ways. Remember absolute extrema? Find critical numbers, endpoints, find high, high, and low, low. First derivative test, relative max and min, and then second derivative test. Remember, if we were concave up, we had a min, concave down, we had a max. Okay, but a couple of things that I want you to notice is the second derivative test showed relative and the first derivative test showed relative. The absolute showed absolute. So how are these all options? Well, look at the directions up here. It says steps to finding the max min. So we are dealing with absolute. But here's what's going to happen. If you have this function, right, and if it goes up and comes down, isn't the relative the absolute? So we can use the first derivative test if we say f is always increasing, then always decreasing. Also, the second derivative test would just tell us if we had a critical number, if it was a relative max or min. But look at, if the function is always concave down, isn't the relative the absolute? Okay, so that's why those are going to be helpful. So as we go through, keep that in mind. We are not looking for relative. And if you just give me an answer saying it's a relative, that's not good enough, right? We want absolute. Like if, I don't know, if a car company wants to maximize their profits, they want the absolute max. They don't want to know in the area if it's the max. So we have to make sure they're answering their questions. These steps right here, again, I'm not going to read them to you. That is so boring. I'll just apply them as we go. But you can go back here and always look at them if it's for your reference, okay? You are going to have the choice to use the first method, the second method, or the third method. By going through the examples, I'll show you when certain methods are beneficial. Method 1, absolute extrema. Obviously, if you're testing critical numbers and endpoints, you have to have endpoints. If you don't have endpoints, then that doesn't help. You can't even use this method, okay? So if we don't have endpoints, we're not even going to try to use absolute extrema. And here's the issue with it. Not every problem will have endpoints. So I try telling you what you need to do, and then I'm telling you, hey, here's the issue and why you might not be able to apply it. Again, these are story problems, but to get used to the methods, I'm just going to use a regular function, and we're going to go through it, okay, to refresh your memory. Again, this is an awesome way to review Chapter 3. Find the maximum. Notice it didn't say absolute or relative, but we know if they don't say anything that they mean absolute. The first method, what you do is you find your critical numbers first. So we need to find our derivative, which is 2x minus 4. We then either analyze when the derivative is 0 or when the derivative does not exist. Because this is a function that is defined everywhere, f prime is, then f prime always exists. So now we're going to set this equal to 0. If that's the case, we add 4 over and x is 2. We then test our critical numbers and our endpoints. And this was back from section 3.1. So we're going to test -3, 2, and 10. We don't test them back in the derivative. That wouldn't make sense. We're saying what is the absolute max on the function. So we're going to sub all these numbers into here. I'll do a couple with you. Like if we want to find f of 2, that's going to be 2 squared minus 4 times 2 minus 12, which is going to be what? 4 minus 8 is -4, -16. F of 10, we sub 10 back into the original function. 10 squared minus 4 times 10 minus 12. 100 minus 40 is 60. 60 minus 12 is 48. You're going to do the same thing from f of 3. If you want to do it on your own, go ahead. It's going to give you a 9. So what would we say? What is the maximum? It has a max of, what is the biggest number? 48. So this function has a max of 48. We're going to test absolute max and min today using different strategies. This is one strategy. Okay, going on. First derivative test. So let's see what's going on with this one. We need continuity. We already said that. After finding the critical numbers, we need to test f prime immediately to the left and immediately to the right. But remember what I told you. This is only giving you a relative max and min. In order to get absolute, look what we have to do. We have to say if the derivative is positive to the left, and then the derivative is negative to the right. So positive to the left, negative to the right. For all x in that interval, then we have an absolute max. This is a special case of relative. It's going to be relative and absolute. Also, look at number 2. If the first derivative is less than 0, then the first derivative is greater than 0. Less than 0, then greater, then we have an absolute min. Okay? So it's just not enough to test relative. We have to test to make sure it's absolute. Okay, both cases we said we need continuity. Why? I mean, we need continuity a lot in calculus, but look at this one. Isn't this the absolute max? But the definition said f prime had to go from always positive to always negative. Well, look at this case. Isn't f prime always positive? F is always increasing and then always decreasing. But this is not an absolute. This is just a relative. Okay, so the whole idea of continuity really throws it off. So this would be lying. Okay, if we follow the rules, it says f prime always positive to f prime always negative. This should be the absolute. But because of this break right here, this is. Okay, so this is why we need continuity, or else we're going to get a false conclusion. Let's use the first derivative test now to get absolute. Okay, how did we get relative extrema, guys? We found the derivative. The derivative is 2x minus 4. After we get the derivative, we set it equal to 0 to find our critical numbers. We also want to see where it doesn't exist, but we saw this is the same quadratic from the first page. One thing too I forgot to mention, always check your domain to start off with. You then did interval testing, and you did the sign of f prime, and then you did the conclusion of f. The interval goes from negative infinity to 2 and from 2 to infinity. Remember, if you make this awesome chart, which I want you to, the sign of f prime, it tells you exactly what to do. Pick a 0, sub a 0 in here and you get a negative. Sub a 3 in here and you get a positive. So what's the conclusion? If f prime is negative, f is decreasing. If f prime is positive, f is increasing. And actually, can you change something in this? This is supposed to say minimum. Okay, so looking at this now, they're asking us for the minimum. They did not say relative, yet we're using the first derivative test, which is relative. So we need this to work out. Look how this is happening and why this works out. If a function goes from always decreasing to always increasing, isn't it this? So even though this gave us a relative min, because the function was always increasing to always decreasing, it's also an absolute. This is a special case. Now, if we also went on, and if the function right here, like let's say it went from always decreasing to always increasing, and then it went on more, do you guys see we could have an absolute min here? But because that's not the case, and because the function, like I said, goes from always decreasing to always increasing, it has to bottom out. The biggest thing about this, that's going to be the majority of your points on this assessment, is writing an awesome statement. You have to say why. That is so important. So we are going to say we have a min of negative 16. How did I know that? Let me go back and show you. We know that the min occurs when x is 2. You have to sub a 2 in. Okay, then we have minus 12. So if we're going through this, 4 minus 8 is negative 4. Minus 12 is negative 16. Okay, that's where I got that from. So we have a min of negative 16. Why? Because from negative infinity to 2, f prime is less than 0, so f is decreasing. Then we're saying from 2 to infinity, f prime is positive, so f is increasing. Remember before, guys, when you dealt with first derivative test, all you had to say was f prime went from negative to positive. Now we have to be more specific because we're saying we're using the first derivative test, but we're actually using it for absolute. So we have to say f prime went from always negative to always positive. Always negative to always positive, meaning relative is absolute. Okay, so you have to be a lot more precise when you're using this one. The last method, second derivative test, I'll tell you right now, this is my favorite. I think this is the easiest of all of these. And as long as I could find the second derivative, I would go ahead and use this. We have the same thing that we're looking at continuity, we're looking at critical numbers. What this is saying is if the second derivative is positive, what does that mean to you? Positive second derivative, doesn't that mean you're always concave up? If you are always concave up, like look what it says, the second derivative is positive for all x, then my relative min is my absolute min. Okay, second one, it says if the second derivative is always negative, remember concave down like a frown? So if we're always concave down for all x, then we have an absolute max. Before we use this in 3.4, and we used it just to test relative. We found critical numbers, we subbed them into the second derivative. Now we're saying, well, if a function is always concave up, my relative is my absolute. Okay, can you guys also change this to minimum, please? Okay, hopefully it's changed on yours. Again, if you're making notes, write this as my favorite. I think this is going to be your favorite also. Again, the only reason is if the second derivative is super messy, we don't want to take this route. Okay, the first step is to find critical numbers. So let's go ahead and find the first derivative. I already have it written down here. We want to find where the first derivative is 0 or does not exist. 2x minus 4 exists everywhere. We're just going to look here. This is the third time we've written this. We know x is 2. Okay, so this is a critical number. It has the potential to be a max or a min. What we're going to do now is find the second derivative. Now watch how nice this is. If this is the first derivative, the second derivative is just 2. Well, what is 2? Isn't 2 positive? So if the second derivative is always positive, it's always happy, the function is concave up like a cup. So we could say for all x, like it doesn't even matter what x we're looking at. For all x, the second derivative is always positive because the number 2 is always positive. So f is, what is f? Concave up. If you have concave up forever, right, always concave up, then this relative min is also an absolute. And find the minimum. So f is concave up. We could say there's a minimum of -16. I'm stealing that from the one above. Wasn't f of 2 -16? So we just did this in example 2. The input was 2. We sub 2 in here, and we get -16. Okay, so these are the 3 methods. Now we're going to go on to using some story problems. Okay, first one, we need to enclose a rectangular field with a fence. We have 500 feet of fencing. There's a limitation. In a building on one side of the field, so we don't need fencing there. So can you guys imagine we have a building on one side, and then we have fencing going around. We have 500 to work with. We don't need fencing on this side with the building. Determine the dimensions of the field that will include the largest area. Or enclose the largest area. Okay, this is totally a real life problem. How would we go about doing this? So what you're going to do, if you go through those steps that I wrote on the first page, I'm going to walk you through them right now. First, I want you to identify your primary equation. You are going to write max or min. If we are trying to find the largest area, we are going to maximize. So we are going to say we want to maximize an area. Now we need some dimensions. So remember when we did related rates, we had to draw variables on our pictures. We're going to do the same thing here, x and y. So we want to maximize our area. Now this has 3 variables, right? This is not going to be helpful. What we're going to do is we're going to come up with what's called the secondary equation. The secondary equation almost always has your limitation, which is this 500. We are limited with 500. So we have 500 equals 2x plus y. I got 2x plus y because we have to add up. We need 500 feet of fencing, so we're going to put some here, here, and here. They told us it's rectangular. That's why we drew a rectangle. Our goal now is to get this primary equation to get rid of one of its variables. We can do that by using our secondary equation, which is right here. I want you to solve this for whatever is easiest to solve for. I hope you can see it's easiest to solve for y. So y is 500 minus 2x. Our whole plan was to be able to get rid of one of these variables. So now we're going to replace this y with 500 minus 2x. So again, recapping, this is the first time we're doing one of these. Write your primary, write your secondary, use your secondary to sub in. This is what we're maximizing, so we have to focus on that one. Okay, so I'm going to have a equal to x, and now I replace y with 500 minus 2x. Now we're down to 2 variables. Now we're ready to rock and roll. We have to find this derivative, but I don't want to use product rule because we can expand this rather easily and get 500x minus 2x squared. If we want to, how do we maximize something, guys? We just did it with absolute max and min. Find critical numbers. So go ahead and take this derivative and get 500 minus 4x. What do we do next? We either set this equal to 0 or does not exist. This will exist everywhere, so we don't have to worry about that case. So we have 500 minus 4x. You can add the 4x to the other side and get an x of 125. Okay, all we did right now is find a critical number. This is like a critical number, but that's not what we want. We have to maximize. So you guys have all these methods now, method 1, method 2, or method 3. What did I tell you before? Do you remember my second derivative is my favorite? Look why. This first derivative is easy, agreed? Because it's easy, isn't it going to be easy to take the second derivative? Method 3 is my favorite. Now, if we had a messy first derivative here, why would we ever want to take its derivative? Method 3, what we have to do is we have to take the second derivative. If you look right here, if the first derivative is 500 minus 4x, the second derivative is just a negative 4. What is negative 4? Second derivative is negative, concave down like a frown. We have an absolute max, and we wanted a max. So this is working out beautifully. We would say for all x. Why for all x? Because it's a constant. If the second derivative is always negative, who cares what x is? For all x, the second derivative is less than 0. So what does that mean a is? A is concave down. We just proved that 125, this 125 here, produces an absolute max because we have concave down. But they didn't ask for just x, they said find the dimensions. So now you're going to go back over here to your secondary. The reason I'm using secondary is because it relates x and y. Okay, so to be able to do this, we have to find out what y is. So we're going to have 500 equals 2x plus y, but 500 equals 2x is 125 plus y. That gives us y is 250. So our dimensions will be 125 feet by 250 feet. Okay, so we have 125 by 250. The 125 was our critical number. We proved that we actually had a max, and then we subbed 125 into x in order to get y. I want to state how important this piece is over here. You getting a critical number doesn't tell me you know anything about 3-7. It tells me you know how to do 3-1. Okay, you have to make sure that you know this method as well. This is going to be to the right, the bulk of your points. You could also use method 1 here if you wanted to. Your endpoints, I'll just give you a little tip, and I'll put this in a bubble. Your endpoints would have been, oh, not f, wasn't it a? Yeah, a of x. You would have had to test 125. You would have had to test the endpoints. So what is the smallest x can be? And these endpoints really don't make sense. It's kind of weird. Couldn't x be 0? So if you take 500 feet of fencing and put it all right here, you have no x's, right? Or you could put nothing here and take 500 and split it here, so your x could be 250. So that's 125, 0, and 250. And then you would sub those into a. So this is method 1, also works. Let me separate this. You could have done this if you wanted to. The notes have it all worked out online if you want to look at that. Okay, or if you want to ask more in class.